Okay, so let's go ahead and get going. We're recording. So let's start out with what lecture is today? 7? Are you sure you're... So this is ee420 / ecg620, and today is lecture 7, and this is spring 2016, and today's date is February 9th, 16. So what I want to do today is just work problems and answer your questions. So why don't we get going with what questions you have? 9.9? Use simulations, generate the plot seen in figure 912 for both NMOS and PMOS. Okay. What if I can't do it? I already did. Yeah. But that doesn't mean I know what I'm talking about. I'm just faking it. All right, so I need to plot the threshold voltage versus VSB. So I'm sweeping VSB. So source to bulk potential is getting swept, and then I'm going to look at the threshold voltage. So what do I know about the threshold voltage? How much current flows at the threshold voltage? It's right where it starts to turn on, right? So I could pick some current like 0.1 microamps or something, and that would be the current that flows. Does everybody agree with that? Okay, so let's see what happens if I do the following. I go to my little folder here. I go, let's pick lecture 4, example 1. Then I go file, save as lecture 7, example 1. Then I'm going to go get the scissors out here, and I'm going to cut. I'm going to call this. And I'm going to get the scissors out here, and I'm going to go ahead and put in a current source. Control R. And let's do Control E too. And let's put this current as, I don't know, something arbitrary. Let's say 0.1 microamps. It's just some small current where we can see the threshold voltage changing. Okay, does everybody agree with that? Okay, so now I'm going to need to generate V source to bulk. So what I'm going to do is I'm going to know the source in this class is, or the bulk is always at ground in this class. The bulk is always at ground in this class for the NMOS. Okay, we've said that numerous times, and I bet your brain didn't pick that up. So if I'm going to generate VSB, what voltage do I need to change? Okay, VB is always ground. I can't change that. Okay, again, I'm repeating myself. The bulk voltage is VS. VB is always ground. Well, I'm going to spend mental thought on that and hurt myself and waste time. No, the bulk is ground, period. Don't think deep. Okay? So I'm going to go ahead and get the scissors out here. And I'm going to move the models to, how about we put them right up here. Oh yeah, and then I'm going to go grab this and I'm going to plop it right there, and I'm going to rename it V source. And I'm going to change its value to 0. And I'm going to get a wire here. And if I run the .op, what do you think I'm going to see? What's that? Okay, one more time. So what's the source potential? 0. What's V source to bulk? That's what's seen in the figure there. That's what's being asked to plot. Whoops. What is this right here? V source to bulk. That's the x-axis. That's what I got to change, right? But what's the bulk voltage? 0. I'm asking you the same thing over and over again. If it doesn't come out quick, you're not paying attention. Okay, so I'm going to make this big. If I put 0.1 microamp, that's not very much current. That's where the valve's starting to turn on. So if I measure this voltage here, what am I going to measure? The threshold voltage. So let's call it VTHN. Let's go ahead and label it. And let's go ahead and let's run the dots, run the sim. Before I look at that, what is the threshold voltage for this device? From the back of the book or table, 0.8. So let's go ahead and put our cursor on there. What does it say there? 0.724. Well, of course, I don't know exactly what current is flowing, but that's in the ballpark. So now I want to plot the threshold voltage, which is always going to be with this 0.1 microamps flowing through it, versus VSB. Tell me what to do. DC sweep. Yay. What do I sweep? I sweep VS. VS from, how about 0, no body effect, to a stop value of 2 in a 1 millivolt step. Okay? Now when I plot, what am I going to plot? This threshold voltage versus VS. Does everybody follow? Yes? Yep. No, because I'm saying, hey, it's 0. But now I'm over here, I'm saying I'm going to override this and go from 0 to 2 volts in 1 millivolt steps. Yeah, if I put this as 1 million, or 10 million, whatever, it's still going to be 0 to 2 volts when I do the sim. Does everybody follow? Any questions? Does everybody see how I'm faking getting the threshold voltage? Okay, this is the problem. This is practical. This is how you do it in real life. This is how you got to make the change in your thought process. How do I go from being an academic to somebody that actually does things? And this is it. How do I get the threshold? I put a little current through there, and I sweep the VSB. Bulk's always ground. So I hit run, and then I plot the threshold. And then what do I got going on? Oh, what did I do wrong? I'm not really plotting the threshold voltage, am I? I'm plotting the threshold voltage plus. What is this? This is VGS. That's the threshold voltage, but it's VGS plus. Okay, what's the voltage here? That's the gate. I'm claiming that's going to be the threshold voltage. So from here to here is a power down. It's like going down a hill, threshold voltage. Then from here to ground, I've called VS. So if I want to plot the threshold voltage, I got to take this voltage, VTHN, minus V of, let's see if it lets me put VS in there. I don't think it will. Oh, it did. Okay. Oh, wait, does that look like the plot? You better say yes. It's just zoomed in. Okay, there's the plot. Oh, it doesn't look like it. I want to make sure I get full grade on my homework. So I'm going to change the bottom to 0, the top to 2, and the tick to 100 milli. Oh, I don't like that. It still doesn't look like the plot. Let's go 1.2. Oh, there we go. I could even make it more look like the plot, couldn't I? Does everybody get the idea? Any questions? Should we save this? Okay, next question. 9.26. Is the book tough to read? Yay! You know, when I'm traveling, there's especially some of the hotels in rural areas are really crappy internet, and I've just given up and I just tether my phone everywhere I go, and then I don't have to spend time on that. And I keep thinking to myself, why aren't I doing this now? And I'm like, they need to provide me infrastructure, damn it. All right. Okay, so 9.26. Use the short channel parameters in 9.2. Calculate the drain voltage for M1, its gate current AC and DC. Oh, this one's so easy. I love it. All right, let's do it. I love it when you ask me questions that aren't challenging. Okay, does everybody see this? It says use the parameters from table 9.2. Do I need to calculate DC currents or voltages? Okay, if I do, I'm not using the parameters from table 9.2. Do I need to calculate anything? Maybe some multiplication of ACs, but what's VDD? What's VSG? 0.35. Threshold voltage is 280. So what's this voltage right there? I'm going to do the problem. 1 minus 0.35, 0.65. Challenging. All right, let's do it. Before I do, let's see. 50 by 2, bias current 10 microamps, VSG, VGS 350, GM is 150 micro, R outs are 167 and 333. We ready? Was that on today's homework? I'll put the new homework in later today, but I wanted to see how everybody was doing before I did that. So how were the lectures? The video lectures? Straightforward? Well, that's what I said, watch the end of 4. You shouldn't have to watch 3 others. You should have to watch the end of 4. All right. So let's look at this. I'm going to change it a little bit. I don't know. Maybe I just can't do it. We'll find out in a sec. These problems, you know. Too easy? Everything's easy when you know it. So let's write the DC voltages first, shall we? Stress and lack of sleep is not good for you. Let's write the DC voltages. Tell me what to start that's easy. What's this voltage? What is the VSG and the VGS? What's this voltage here? What am I the king of? Trivial questions. What's this voltage here? What's this voltage here? Did I go over that too quickly? Questions? I'll do that next. Before I do, are there any questions? What are the currents through here and through here, DC? What's the relationship between here and here? What are the VGSs of the two NMOS? What is the DC? We're talking DC. What's the relation between the DC VGSs? They're the same. I don't ask hard questions. Okay? What is the current flowing through this transistor? 10 micro. How do I know the current through here has to be the same? Same VGSs. Any questions about this before we go over and do AC? So when I calculate the AC voltage here, the overall voltage will be 0.65 plus the AC. Do you want me to start asking hard questions? You do? I don't believe you. Okay, so let's go back. Any questions here? Even if you don't understand, please ask me. I mean, so we do have a quiz today, but because the issue is starting at the beginning, I'm going to give it to you as a take-home at the end. And I want it to be nice and clear, not sloppy, and I want you to turn it in when we come back on Wednesday or Thursday. I'm so used to teaching on Monday, Wednesday. And I'll treat it as a normal quiz, all right? And it's not meant to be challenging. You can look up the answer. What it's meant to do is make sure you understand the concept, so when I give you a quiz on Thursday, you do well on that quiz too. I'm not trying to trick you. Okay, so let's redraw the circuit again and do the AC. I know you're not used to that. Before I continue writing this, how much AC current flows through the 20 microamps and why? Why? 0, right? It's a constant source. I can't change any of the current in that source. Does everybody understand that? So when I do an AC analysis, how does that source come into play? No. If I don't have any current flowing, here's my 2 fingers. How much current flowing in those between the 2 fingers? What do I call this, the between the 2 fingers in circuits? An open. Does everybody follow? So when I go draw, there's no current flowing through there. It doesn't influence the AC circuit. When I go draw the AC circuit here, how much current, what should I put here for the current source? Nothing. No current flows through there. So everybody got that? So I'm not putting it there because it doesn't influence the AC. I do the DC with the AC source shorted. You notice when I said, what's the voltage here? It was without that AC source. Everybody follow? I short it out, superposition. When I say it's 0.5 volts, that's assuming the AC is not present because we know it's not 0.5 volts. It's 0.5 volts plus the AC. But I'm doing the DC calcs. So I'm going to go over here. Oops. I'm going to go over here and I'm going to ask, what is the AC voltage there? How do I wiggle that 0.5 volts? You can't. So if I can't change a voltage, that's a short. Well, wait, can I change the voltage between my 2 fingers with no current flowing? Sure I can, because it's an open. I can change the voltage across open. I do it all the time with the outlet there. It's going 120 volts RMS, 377 peak to peak, 60 hertz. Change it all the time. But here, I don't change the voltage, so that's a short. So I'm going to replace that gate, the 0.5 volts with the source, with the short, and I'm going to put my AC there. I'm going to replace the other 0.5 volts with the short. What about these 1 volt sources here? What do I connect those to? They don't change as well. And now I want to pause and talk about this because this circuit's confusing. At least it was when I was learning. We're going to talk about this voltage. And you should have saw this in the video too. So it's a little bit of a repeat. This voltage is what? If I call this M1 and this M2, what's this voltage? VGS1. What's this voltage? So if I write of KVL, we can even short these together if it makes you feel good to have circuital. I can write the loop as what? See, I would have written it, but see, I would have written it like this. So this is plus minus, so I would have picked that's a power up, and that's equal to power down, power up. But either way works, right? Any questions? Okay, so what's the DC current flowing in each of these? What is the DC current flowing in each of these? 10 micro. So I've got 10 micro and 10 micro. When I say there's a current, let's say I calculate the current and I say it's 0.1 microamp. And it's going backwards. Let's say I draw it going up like this. That means that 10 microamps is going from 10 down to 9.9. But I draw the AC as subtracting from the 10. Okay, I'm going to go over this again in a second, but before I do, if I draw a transistor like this, and I say there's 1 millivolt there, just like that, what's the current AC that flows, assuming I'm in saturation? GM times VGS. Any questions? Everybody? Yes? Yeah. No, I'm not. Because when we draw the current, we're going to get a current that flows like this. We're going to call this ID1. ID1 flows up, but I define ID2 as going down, and that's minus ID1. And so you might ask, well, wait, how can current flow from the source to the drain in a MOSFET? It's not. The overall current is decreasing. So when I draw current flowing backwards, it means the overall current is dropping. But we don't see that in the AC alone. We see it flowing backwards, and that's not what we think. At least for me, when I was like, how the hell can current flow from the source to the drain? Current flows from the drain to the source. Well, it's not. The AC current's decreasing, but the AC current's flowing backwards, but the overall current just simply means the overall current's going from this down to this. Yeah, when you add the AC plus the DC, you add them together, that just means the overall. And we'll do this in a second. So how do I proceed? I got 1 millivolt. I don't know that. They have the same current, so we could draw that conclusion because there's no other place for the AC to flow. That doesn't mean that this VGS is equal to this one. It does if they're the same sizes, but I could give you a problem where this is slightly different in the current, and then the VGSs wouldn't be split. So tell me what to write. Wait. Don't make it hard. Do you agree with that? Does everybody agree with that? I'm not making it hard. I'm making it easy because I want to get full credit. But then I realize, where else can the ID1 flow? Everybody agree? Questions? So now what? Plug and chug. So I get ID1 over GM1 minus ID2 over GM2. Now what? Well, let's write it like this. Does everybody agree with that? But wait, what is the relation between GM1 and GM2 and why? The same. Why? Same DC current, same sizes. We know GM is equal to the square root of 2 times Kp times W over L times ID. If they're the same size, they have the same current, they have the same GM. Oh wait, but I also know GM is equal to Kp times W over L times VGS minus V threshold N. These are equal. They have same VGSs, same sizes. They got to be equal. Yay or nay? Does everybody agree? So I can say that this is equal to ID1 times 2 over GM1. Yay? Tell me what to do now. Well, I know GM. How do I know GM? I don't have to calculate any. It's in the parameters. This is 150 micro. Yeah, that's right. ID is equal to 1 millivolt divided by 2 times GM. And what's GM1 from the book? 150 micro. So let's see, that's going to be 75 micro, because I divide by 2, times 1 milli, which equals 75 nanoamps. And before I go any further, I want to prove it. Yay or nay? So if it's 1 millivolt peak, it's 75 nanoamps peak. If it's 1 millivolt RMS, it's 75 whatever this is, this is. If it's peak to peak, then it's 75 nanoamps peak to peak. Yes? Yeah, so since this current has to equal this current, the VGSs are the same, so this will be 1/2 millivolt. This will be minus 1/2 millivolts, so let's write that on there, which we can deduce by just doing this loop equation here. This would be 1/2, this would be 1/2. So the potential from here to here is 1/2 millivolt. The potential from here to here is 1/2 millivolt. Notice plus minus sums to 1 millivolt. Does everybody see? So if I ask you what's VGS2, minus 1/2 millivolt. Stare at these because once you learn it, it's trivial. Before learning it, it's tough. So you see, oh, this voltage from here to here is 1/2, but the voltage from here to here is then opposite that. Yes? Yep. If they have the same current, yes. Yeah. There's lots of things that I could do that would make it easy, but I'm trying to make sure that if you have some, like I change the size of this, you can solve it. If I make this voltage 0.51 instead of 0.5, you can solve it. All kinds of things. I want to show this 75 nanoamps before we calculate. So what's the AC voltage right here at this point, just as a sanity check? Plus minus to ground, 1/2 millivolt. It's 1/2 millivolt. What's the AC voltage right there? 1. What's the AC voltage between here and here? 1/2 millivolts. Everybody follow. Okay, so I want to go do this sim real quick and prove it. Then we'll come back and calculate the last AC voltage, which is what? Where's the only AC voltage we haven't calculated? This one, right? Or this one, they're the same voltage. Does everybody agree? Okay, but let's go do the 75 nanoamps. And since you've been looking at the SPICE files, is there one? Yeah, I'll just do it from scratch. It'll only take me I'd rather not. Is there one I can cheat? 919? Nope. can't because that's all the larger devices. Let me just do it from scratch. 918? 918? Wait, what was this one? 918, there is no figure 918. Let me just pick one here then. Rely on myself here. Let's see how fast I can do it. What is a 50 by 1 device, or yeah, is it 50 by 2 device in the short channel process? What's the size? That's right, 100 nano by 2.5 micro. Yep, that's correct. And then the model name is N_50N. Am I assigning enough homework in this class? No? No, yes? Can you get the project already? I'm really not moving fast enough, huh? And then let's do a couple voltage sources. Is everybody becoming spice gurus now? What's that? By the end of the semester? How many classes have you had with me that use LT Spice and you're not a spice guru? Oh. Did you forget everything after cadence? Come on. Ah, okay. Then you'll have forgotten cadence. Yeah, I love being having to come to school to use the tools. That's really great. You just slow the internet connection at home, and now because someone attacked had it attacking the internet, basically our server, somebody's account got hacked, and they now make you VPN in. So yeah, I know, that's the problem. Yep. And this one, everybody's probably thinking it needs to be 1 volt. And let's change this to VDD so you have nice, good. And then let's go do the following. Any questions on what I've just done? Is anybody bothered? I haven't shown these. Are these the right sizes? What? And that's not 100/2? You guys are scaring me. So what does, in the short channel process, what does 100 mean? Means 50 nano times 100. Are you looking at the example? Isn't that right? Okay, so how am I going to determine the AC value? Let's do it 2 ways. Let's do it with an AC. Let's go put an AC amplitude of 1 milli right there. Let's do a right-click AC, decade, number of points 100, start frequency 1, stop frequency 1K. Hit OK. Anything else we need to do? We can label some nodes. I'm not going to because it takes too much time. So I hit run. Nothing succeeds like success, so why don't we start by plotting this? I don't like dB, so I'm going to change it to linear. Okay, 1 millivolt. Now what? Let's plot this one. It's slightly less than 0.5 because I've got body effect here. And if you don't believe me, go home and connect these bodies over here. But of course, that's not the way we're doing things in this class, because body's always connected to ground of the NMOS. Not of the PMOS, but of the NMOS. So now I'm going to do add plot plane. Then I'm going to plot the current. Boom. And it's 86 nano. That's a little bit off than what I was guessing, but in the ballpark. If I wanted to find what the GMs and the R outs were, refresh my memory. For a dot OP, right? You do a dot OP, and then you look at view spice error log, and it tells you what the small signal parameters are for every device. Again? No! You can do it on your own. I did it last time. Yeah! Killing me. I recorded it. Alright, so let's do one more. And let's close this. And then let's go here. File, save as. Example 3. Now I'm going to do a transient. I'm going to do right click here. Change this to a sine with a DC offset. Excuse me, a 0.5, an amplitude of 1 millivolt, a frequency of 1 kilohertz. And then I'm going to hit, oh, the grader graded your homework. I didn't grade them, and he was a little bit crazy with the points. So I took his points and divided everything by 2 so that that homework wasn't like worth 3 other homework. So that's why you see the divide by 2 on there. All right. And then what do I do next? Change it to .tran. Let's stop time. Let's do 5 cycles. What am I guessing is going to happen this time when I run the sim? It's going to be jagged. I didn't put the dot options, plot win size equals 0 in there. Let's see what happens. Okay. Hit run. Nothing succeeds like success. Oh, no. Let me waste a half hour on that. Does everybody think that looks right? Is the DC what we calculated? What is the DC? What's the DC voltage at that node? 0.5 volts. Does everybody see the signals writing on 0.5 volts? Okay, so what am I going to ask next, since I'm the king of repeating myself? What's the AC? 1 millivolt. I see it goes above the DC by 1 millivolt and below the DC by 1 millivolt. Is this challenge anybody? No? What am I going to plot next on this same plot, since I'm doing exactly what I did a second ago? Source. Boom. Wait a sec, I can't see them. Why is that? But the AC before was 0.37, and now the AC's at 1 millivolt, but I can't see them together. Why not? What? Yeah, but why can't I see them before I do the new plot plane? Yes. Well, one's 1 millivolt AC, the other's 0.36, but why can't I display them on the same plot? What's that? Yeah, there's different DC voltages. This DC voltage is 0.35 volts lower than this one. Well, plus body effect, it'll be a little bit more. I'm doing exactly what you would do when you're solving the homework, and I'm showing the problems you will have, like when you click things, why didn't it work? Well, the DC is not 500. I can't compare something up at 500 and something at 120 when the amplitudes I'm looking at are a millivolt. I won't see anything. So I'm going to go right. It's not confusing. It's the DC voltages are different. I'm going to add plot plane. I'm going to drag the sources up. And there I see, hey, I'm roughly at 124.78. And then I go up. So you know what? I don't like that. I'm going to do minus 0.12478. Oh, that's what I had before. Same exact answer, about 350 micro. Oh, I don't like this either. I'm going to do minus 0.5. Hey, that's what I had before as well. Now what am I going to plot? Current. So I'm going to add plot plane. Then I'm going to plot the current. But what do I expect I'm going to see? I'm not going to see AC plus DC. They were just in concert last Friday night here in Vegas. So what do I do to see my 75 or 80, whatever it was, nanoamps? I'm not confused. My AC is riding on DC. I don't have magical AC without DC. I'm turning the faucet back and forth and looking at the wiggles. 9.1 E. How about let's not use E6. Let's be lazy and use U. Oh, there we go. Is that close to my 75 nano that I calculated? Sure. Let's hit save. Any questions on this? Yeah, the .ac, I can sweep the frequency and look at a frequency response. Here, I can't do that. It's the time domain. Time domain's good for looking at distortion, but an AC is good at looking at frequency response. See, at an AC, everything, all the devices are replaced with their small signal models, meaning resistors, capacitors, voltage-controlled current sources, the model. But in transient, they're not. They're actually the devices. So if I'm going to design like an audio amp, AC is okay to look at frequency response, but if I want to look at how good the distortion performance is, if it sounds good, I got to do a transient. I'm just showing you different ways of doing it. If you did it with AC on the homework, that's fine. Yeah, I'm just trying to make sure that you don't have a low quality education. Did you do dot plot win size equals 0? Maybe I should put some examples on. Oh wait, I already did. I don't know what to say. Okay, thanks for letting me know. Okay, let's go do the last part of this example, then we'll work one more. So next week I have to travel again for the college to NASA and to the Army base to do some demo stuff. So I really don't want to give videos assignments again. That's a slippery slope. So what I'm thinking is that we meet on like Sunday and do a makeup lecture, and I'll record it. So if you can't show up, then you can watch the video. And then in the following week when I'm back, I'll set a time on like Friday afternoon, so that if, or maybe late afternoon, so that if you can't make it then, you can watch the video as well, because I don't want you watching last year's video. Does that sound good? All right, and if you can come, that's great. If you can't, that's all right too. What's that? I don't know. You know, the thing is, like, I had a student telling me yesterday, "Oh, I didn't take your class because I have a class at 4 and yours is at 10, and it would be a long time at the university." And I'm like scratching my head, "Are you flipping kidding me? You got 6 hours. I could, if you don't have to work or whatever, I could study. There's so many things I could figure out to do. I don't understand what the issue is." So, anyway, what's that? I think that may be it. Well, I could take your class, but the pain is high. You actually expect me to learn. I don't like that. Okay, I'm only going to draw the PMOS portion. And this voltage is AC what? And what do I call this voltage for AC? I don't ask tough questions. Okay, so what is this voltage here? And how is that related to VSG? How do I know that? Okay. So how do I proceed? Let me ask some questions. What's the DC current flowing through there? What's the AC current flowing through here? Any questions on that? Okay, so tell me what to do. What's the current? What do I call the current through the MOSFET? What variable name? So what's ID equal to here? I'm boring you, I apologize. How do I relate this ID to the VSG? I write this down because I'm learning. But what is the GM for the PMOS in this process? And I don't know VSG, but I know ID. What is that? So what is VSG? What's 75 over 150? Yay? So should we prove that in Sims? Yeah, let's do it real quick. Yes. No, that's right, but the VG equals minus 1/2 millivolt. It's this. Is everybody cool with that? Any questions? Another magical, he did magic in class. I don't believe him. He doesn't know what he's talking about. Could you see me in my little table there? Got my busker position. I'm working equations. Everybody would be like, what the hell's wrong? They'd probably give me money just because they felt sorry for me. Okay. Okay, so let's run this. And this is the AC sim. I'm going to go ahead and add a plot plane here just because I love adding plot planes. And then I'm going to plot the voltage here. What do you expect I'll see? It's AC, so is there a minus? So what am I going to see? 0.5 millivolt with a phase shift of 180. I know what I'm doing. Yay! Questions? Close. Let's do the next one. Hit run. Okay, so what am I going to see when I plot this? 650 millivolts. Let's do add plot plane first. Wait, it's going down instead of up. What does that mean? 180-degree phase shift. So when the input goes up, the output's going down. Wait a sec, does that make sense? Let me pause on that. Let's go back here. And let me just draw that part of the circuit. If I drive this voltage up, what does it do to this transistor? If I turn the faucet on more in my house, turns it on more. Does everybody agree with that? If I pull more water through this pipe, what happens to the pressure drop across here? Gets bigger, so what happens to the pressure here? If I have 60 psi going into my house, and I turn the shower on, flush the toilet, and turn 2 drains on, so I'm pulling more water through here because I turn on the valves more, what happens to the pressure drop here? Goes down, so what happens to this pressure drop? It goes down as well. So the pressure drop here, say I had 20 psi, I turn on my shower, flush my toilet, turn the sinks on, and it goes to 30 psi. What happens to the pressure here? Goes from 40 down to 30. Don't think deep. If I have 1 volt, 350 millivolts, I turn the device on more, I pull more current, this goes down. Does that mean when my input's going high, my output's getting pulled down? Let's see. My input's going high, my output's dropping, the pressure's dropping. You need to look at these and make sure you're not seeing magic and you understand what's going on. Any questions? Did I cover that one good enough? Another question. Anything that wasn't clear? Ask me anything. Yeah, I'll go over that right now. Temperature stuff. Sound good? So how many people haven't heard of the thermal voltage from microelectronics? KT over Q. What's K? Oh! Boltzmann's constant. This is what's in my mind. They go for a job. Hey, I want to work at Intel. I'm going to apply at Intel. I got a phone interview. So what's, thermal voltage? Yes. What's KT over Q? Volts, Kelvin. Did you get a good education in 320? Yes, sir. All right. All right. Boltzmann's. What's Q? Charge of a electron. What's T? Temperature in Kelvin. So how do I plot that? Boom. There it is. That was tough. What's room temperature? What is it? 27? That's pretty warm, but yeah, it's in that ballpark, right? So we might have at 300 degrees, that might be here, I don't know what that is, like 90 or whatever. I can't wait to try my old lapel mic out so I can hear better. Any questions on this? Oh, and what is that roughly at 300 degrees? About 26 millivolts. Any questions? Common interview question. How does thermal voltage change with temperature? It increases with temperature. How does VT change with temperature? See, you need to be clear, because I actually had a student ask this in an interview, and they said, oh, you don't know what the hell you're talking about. They were saying VT is this. That's the variable for thermal voltage. He thought they were asking about threshold voltage. So when they ask, you say thermal voltage goes up with increasing temperature. Threshold voltage decreases with increasing temperature. And we'll talk about that right now. I want to simulate though. Tell me how I can simulate what the threshold voltage does with change in temperature before I discuss it intuitively. I want to see if my efforts today as an educator have yielded results. That's how you get people to manipulate people with statistics. You ask leading questions like that. So I'm going to go File, Save As, and let's call this example 4. Is it example 4? Or is it 5? Done so many examples in this class. And we don't need this anymore. We're not changing the threshold. We're not changing, right? So is everybody cool with what I just did? So is this roughly the threshold voltage, putting a little bit of current flowing in the hose? So here, I'm going to teach you something neat here, unless you know it already. Did you have a homework problem on temperature yet? So how do I plot temperature then? Dot temp? Yay! How about 0 to 100 in 1 degree steps? So I'm not teaching you anything. You already know this. Whoops. That's is it .dc temp? It's not. Let me see what happens when I do this, just for the hell of it. Ding. Is everybody cool with that? So what does the threshold voltage do as temperature goes up? Okay, so this is a big problem nowadays because you know your processors, your mobile phones, all those things have lots and lots of transistors. As you put them, as they are used, they heat up. Or you leave your phone in the sun, or you're in Las Vegas, it's in your back pocket and it's 120 out, right? That makes the threshold voltage decrease. What happens to the leakage through the transistor as temperature increases? And then what happens? Yeah, it goes up. The battery drains. So this is a huge problem nowadays in your electronics because the threshold voltage dropping allows more leakage to occur with temperature going up. Any questions? Okay, so I'm going to briefly, because we cover this in more detail, tell you why this happens. We cover it in 421, the digital class. As temperature goes up, you get more electron generation. It becomes easier to invert the surface underneath the MOSFET gate oxide. So the threshold voltage that you have to apply decreases. You don't have to work as hard because the thermally generated carriers are larger. Okay, does everybody follow that? Okay, I don't expect you to get it. If you take 421, we cover it much slower. Any other questions? We got 5 minutes. Some other question? Yep. No, because you put a VDD up here. So the VSG was decreasing, but here, let me show you. So this is a good question. So if I take the PMOS and I do the following. And I plot this voltage as temperature is swept. What happens to the VSG as temperature sweeps? Let me ask a simpler question. If VSG goes to 0, what's this voltage? If the potential between here and here is 0, VSG goes to 0. It's 1 volt, right? If VSG is 0.35, what's this voltage? 0.65. So if VSG gets smaller and smaller and smaller, what happens to this voltage as temperature goes up? If I plot this voltage as temperature goes up, what happens? Gets bigger and bigger and bigger. Why? VSG is getting smaller and smaller and smaller. Does everybody follow that? No? Yes? Cassandra? All right, makes sense? So what you would do to fix that, you'd plot this voltage and then you'd say 1 minus this voltage. You'd say this voltage minus 1 to plot the overall threshold voltage. Tricky? Yes? Any other questions? Some other questions from chapter 9. There are no other questions in chapter 9. Everybody understood how. Let me just ask questions. So when I ask them in qualitative form, if ID goes up, what happens to the gain, GMR out? Did you watch the videos? Let me ask that. So what happens to GMR out? Goes down. Well, of course, it's not right if you say the... Did you see that in the video? Nobody has questions. I covered that, didn't I? So nobody has questions on that? Prove it. Prove that this is true. GM is equal to the square root of 2 Kp times W over L times ID. R out's equal to 1 over lambda ID. If I look at GM R out, I get something proportional to 1 over the square root of ID. Does everybody agree with that? So if ID goes up, what happens to the open circuit gain? Is everybody cool with that? That was like, to me, when I was first designing, I was like, I need more gain. So I'm going to jack up the current. And it always caused the gain to go down. That's why. How does W influence the open circuit gain? It doesn't. Yay, you watched the video. How does the overdrive, VGS minus V threshold N, which is the overdrive, how does that influence the open circuit gain and why? Okay, let me ask this. If I increase the overdrive, if I increase VGS, this is the amount that I'm above the threshold voltage. If I increase this, what happens to the drain current? Here's what's, yeah, I'm asking you, if I turn the faucet on more, what happens to the water flowing in the hose? Goes up. So if I increase the overdrive, what happens to ID? What happens to GMR out? Goes down, yes. What about speed? FT. Yeah, ID goes up, FT goes down, FT goes up. If I increase VGS, the overdrive, FT goes up. If I increase V overdrive, but it's the same thing as increasing VGS because it's just VGS minus the threshold. What's the only parameter I can tweak when we're out of time to increase both the speed and the gain? The length of the transistors. Go review that stuff and be ready to answer questions because I think we're getting close to moving on to chapter 20. But I want to make sure that you have chapter 9 down. Okay? So let me give you your quiz